So I am Manpreet Singh from Mohali. So today I will speak about the algebraic structures in knot theory. So a link is basically a smooth embedding of disjoint circles in a orientable three manifold. So basically, link by link we mean just a collection of simple closed curves in orientable three manifold. And by a classical knot theory, we mean whenever three manifold is either three sphere or a Euclidean three plane. Now, if we have two knots in a three sphere, then we want to define the notion of equivalence. So basically, if we have two simple closed curves, uh, we know that if we just move them slightly without crossing itself, so they must be same for us. So basically, we want to say this in terms of mathematics. So basically, we say that two links are equivalent if they are related by an ambient isotopy. So basically it means that if we have a two links f and g, then they are equivalent if there exists a continuous map such that it is identity at time 0 and at each time it is a homeomorphism, and at time 1 it maps one link to the other link. So by a link diagram we mean a generic projection of a link over a sphere or a plane. And in bigeneric projection, we mean the only multiple points in the projection are transversal double points. So here is an example of a trefoil projection of a trefoil node and a figure 8 node diagram. So here in the projection at these points, so we are indicating the under arcs and the over arcs. So now we will define the equivalence of two links in terms of the link diagram. So let Mr. Prove that two links are ambient isotopic if and only if their diagrams are related by these three moves. And these moves are known as Redmister moves. So now I will define what we mean by quandras or distributed group words. So first let me motivate the definition of these objects. Suppose we have two types of crossings, this kind and this kind, and we have some set x. Then we want to define an operation over the set such that it becomes invariant under the Redmister moves. So basically, suppose we are taking elements from the set x, say A and B, and we define the rule how define the rule how the underarcs means how the overarcs act over the underarcs. Suppose we have a underarc say label B and we label the overarc with label A. Then we define the outcoming arc as B star A, and if the crossing looks like this, then we define it as B star inverse A. So if we want these conditions, the set to be invariant under the Redmister move, so basically we need these conditions. So if we apply the first Redmister move locally, then basically this arc is basically say x. Then this kind of crossing we get x star x. So basically, if we want it to be invariant, we basically want that this x must be same as like x star x. And similarly, under the Redmister second move, if we have a labeling x and y and we apply the Redmister move 2, then the outcoming arcs are basically y and x star inverse y and star y. So basically, we want that this element must be same as x. And similarly, in the third Redmister move, so basically the outcoming these labels are the same labels. The only difference is at these points. So basically, we formulate the axioms of quandars like the first axiom is basically the idempotency, the second is basically the existence of inverse, and the third is about the right distributivity. And these axioms are basically arising from the Redmister moves. So let's go through some examples. Suppose we have some set x which is non-empty, then just define x star y to be x for all elements in the set x. This type of set is known as a trivial quandle. So notice that any trivial quandle can have any number of elements. Suppose we have a group G, then many examples of quandles can be given from the groups. So first we define the conjugation quandle. So we define the operation x star y as y inverse xy. So basically this is the operation inside the group G, the dot operation. and one can check that this under this operation G becomes a quandle, and we name it as a conjugation quandle. And similarly, the core quandle, in the core quandle we define the operation in this form, y x inverse y, and these are called core quandles. Now a coset quandle, suppose we have group G and a subgroup H of a G, and we had taken some element, say Z, and the condition is that H is contained in the centralizer of the Z. Basically that centralizer, by we mean that those elements of the group which commutes with the G, Z. And we define the operation over the cosets of H in G in this way, Hx star Hy, we define this operation, then one can check that the operation is well defined and this set become a quandle, the cosets become quandle, and we denote it by GHC. Similarly, one can extend this example to disjoint union of cosets in the same way. Similarly, if we have a group and we take some automorphism of the group, then we define the operation x star y as phi x y inverse y, and these quandles are basically known as Alexander quandles. So now I will go through the construction of node quandles. So these are given in the paper Distributive Group Pads in Node Theory by Asmatveev, and in the paper Classifying Invariants of Nodes by David Joyce. So we take an oriented node in the oriented three sphere, and we take a tubular neighborhood and take the closure of the tubular neighborhood, and we take a point. We denote this. We say this set is basically node complement, and we take a point in the node complement space Ck, and we define a set Qk as a homotopy class of paths with initial point on the boundary of the tubular neighborhood and whose final point is at point x naught. And during the homotopy, we allow that the initial point is allowed to move freely over the boundary. Now we define the operation on this set Qk as like this. If we take a two representatives, alpha and beta, we define the operation as alpha composed beta inverse and beta 1. So diagrammatically it means that suppose we have the node K, and this dotted line represents over node K, and these lines represent the boundary of the tubular neighborhood, and we have two elements in the set Q, K, alpha and beta at ending at point x naught. Then the operation is basically we first travel along the path alpha, then we go along beta inverse, and then we move around the meridian. So basically meridian by means a simple closed curve whose linking number is 1 with the node, and then we go back through the path beta to point x naught. Okay. So yeah, one can check that under the operation star, Qk becomes a quandle, and these are known as node quandles. So Matveev and Joyce proved that this is the link. So I have given the construction for node quandles. Same construction can be extended to link quandles also, and they proved that the link quandle is a complete knot invariant for the non-split links. So by a complete knot invariant, we mean up to the orientation of the link and the NP space. So that is, so if we have two isomorphism between two node quandles, so that means that either the nodes are ambient isotopic, or we need to change the orientation of the node and take its mirror image. So basically mirror image means we are changing the orientation of the ambient space. So here is an example how to write a presentation of a node quandle. So we have a trefoil node diagram. So we label the arcs with A, B, and C, and we follow the same rule as we have seen before. We label the arcs A, B, C, and we write the relations at each crossing points. So basically, if we travel along this, so at first crossing, we are getting A to B by acting C. So basically, this is an active crossing. So we get the relation B star C equal to A. And similarly, the second and third crossing, we can get the relations. So unnoting problem. So it is basically a problem in a computational topology. So basically, it is means to detect a node whether it is unknot or not. So then prove that a node is trivial if and only if its fundamental group. Fundamental group, I mean the fundamental group of the node complement space is isomorphic to the integers. So then formulate the word problem. By word problem, I mean So suppose we have a group G defined in terms of presentation X and R. So X is a set of generators and R is a set of relations. We take two words in the written in the terms of X, disjoint union X inverse. So X inverse by we mean a set of formal inverses. So the word problem is to decide whether the two words are equal or not in the group G. So then prove that the word problem is solvable for node groups. So thus we can, so what it basically means that if we are given a presentation of a node group, we can detect from the presentation whether the node is trivial or not. So basically we need just to check that whether this commutator equation holds for every generator or not. So Winker proved that a knot is a trivial if and only if its involutory knot quandle is trivial. So basically, involutory knot quandle basically means that the quandle whose actions from the right are involutory actions, and there is a conjecture that a k is if k is a knot, then its involutory knot quandle is relatively finite. This conjecture is formulated by Fish and Disitasa in this paper. So basically, the aim for formulating this conjecture is basically to work on the word problem. This means to work on the annoting problem. So basically, let me just define what we mean by relatively finite quandle. So basically, it means that we have a quandle and we take any two distinct elements. If we can find a finite quandle and a homomorphism such that their images are distinct in the image. Uh, For example, finite quantals are relatively finite. One can so by definition, and trivial quantals are also relatively finite. So we have proved that in the joint work with Professor Valerie Bardkov and with my supervisor Mahinder Singh, we proved that if G is a relatively finite group, then the conjugation quantal and the core quantal are relatively finite. So the same definition one can define relatively finite groups. Basically, we mean if we take an element and non-identity element in the group G, we can be find a finite group and a homomorphism such that the image of the non-identity element is non-identity. So from this we deduce that free quantals are relatively finite. Basically, free quantals are actually sitting inside the conjugation quantal of the free groups, and free groups are known to be relatively finite. So we also prove that if Q is a finitely presented quandle and it is a relatively finite quandle, then the word problem is solvable. And it is also proved by Belk and MC Gray that the word problem is unsolvable in general for quantals. So I hope everybody knows that the link group is actually a relatively finite group, and in that we have proved that if we are given a quandle a link and we construct a link quandle, then every link quandle is relatively finite. So here is the outline of the proof. We first consider two cases. For first case is basically non-split links. So Manpreet and Joyce prove that if we have a link, then it looks like basically coset quantums basically. So pi 1 means the link group, hi means the peripheral subgroups, basically means how the tubular neighborhoods, the fundamental group of tubular neighborhoods are sitting inside the link group, and mi's are the corresponding meridians. So using this, and the second condition is that each peripheral subgroup is actually finitely separable in the link group. This is actually we deduced from the paper by Long and Niblo. And third is we have proved that if, okay, so what we mean by finitely separable. So we take an element in a group G, which is not in the set H. And if we can find a finite group F and a homomorphism, so here is F actually, sorry, such that phi G doesn't belongs to the phi image in the phi, of the phi H set of the H set. So we prove that if we have a quandle as a coset quandle and HHI is finitely separable in the group G, then the quantity is relatively finite. So basically this implies that all split links are the so basically all link quantiles corresponding to the split links are relatively finite. So for split links we need to look at the free products. So if we have any quantile Q, then to each quantile we can associate a group which is also known as enveloping group or adjoint group and also associative groups, which is generated by the set Q, and the relations are of this kind of conjugation type. So it is proved by Matveev and Joyce that if L is a link, then the associated group of the link quantile is basically the link group. So we have proved that if we are given a family of quantiles which are residually finite, then their free product is residually finite provided their associated groups are residually finite. So we need a hypothesis here. So this basically means that link groups are residually finite. Why? Because if we have, so we have settled the case for the non-split links. So if we have a split link, so basically the link quantity is basically the free product of the uh, link quantiles to non-split links. So basically, since we have proved that the free product is residually finite, provided the link group, provided their associated groups are residually finite, and it is well known that the link groups are residually finite. So we conclude that the link quantile of any given link is a residually finite quantile. So it also means that the word problem is solvable for link quantiles. So here is a one problem. So the problem is basically to prove that the free product of residually finite quantities is residually finite. This problem is the answer to this problem is affirmative in case of group theory, but we don't know whether this is true or not in case of quantiles. We have proved this problem for a finite quantiles. So basically, what we have proved that if we have a collection of finite quantiles, then their free product is always residually finite. So next, we will move to the orderability of quantiles. So so a quantile is said to be left orderable if we can define a strict linear order on the set Q such that if x is less than y, then it implies that z star x is less than z star y for all x, y, z and in Q. Similarly, we can define the right orderability, and similarly we say a quantile is bi-orderable if there exists a linear order such that it is both left and right ordered. So some examples, trivial quantiles are right orderable, one can easily check, but they are not left orderable if the trivial quantile has more than one element. And suppose G is a bi-orderable group, then it is proved by the uh, by in this paper compactness of the space of left orders that the conjugation quantile is right ordered. And if G is bi-orderable, then the core quantile is left orderable, and it is proved by Bardakov, Passi, and Mahendra Singh. And in we have proved that uh, so in these papers there are no examples where it is give of quantiles which are bi-orderable quantiles. So in our paper we have proved that the Alexander quantile is bi-ordered provided the U is basically from 0 to 1, and the automorphism of the set R is defined in this way, and the order over this quantile is basically induced from the linear order on the real line. So in orderable groups, so basically it's well known that braid groups are left orderable, pure braid groups are bi-orderable, and it's also known that all link groups are basically left ordered. So the question is, what can we say about the orderability of link quantiles? So basically one can expect that since the link groups are left orderable, then the link quantiles are either left orderable or right orderable. But we have proved that for the trefoil knot, the knot quantile is neither left orderable nor right orderable. So quantiles behave quite in a distinct manner from the basically from the link groups basically. So There are also link quandles which are right orderable. So the examples are basically 5 but prime nodes whose roots of Alexander polynomials are real and positive. Then these quandles are basically right orderable. So in the joint work with Hitesh Rondal, Mahinder Singh, we have proved that um, many torus links are basically not right orderable. So the condition is that m and n are positive integers greater than 2, and one is not a multiple of the other. So the application of this result is that one can actually, from this result, one can get that the knot group of a non-trivial torus knot is not biodrable. From the this is proved by Perrin and Rolfson. So how we are getting this? So basically, it was proved by Ryder that a knot is a prime knot if and only if its knot quandle is embedded inside the conjugation quandle of its knot group. So we know that torus knots are basically prime knots since are prime knots, and suppose the for torus knots the link group, so the knot group is say biodrable, then we have then it is proved that the conjugation quandle arising from the group will be right orderable. So if it is biodrable, then it basically means that for torus knots the quandles must be right orderable, but our result proves that this is not the case. Okay. So now I will move to our third work, marked ghost diagrams. So this work is in is in collaboration with Professor Valery Bardakov and Professor Mikhail Nestedin. So by a ghost diagram, we mean a finite number of circles oriented anti-clockwise with finite signed arrows whose head and tail lie on the circle. So here is an example. So we have two circles oriented anti-clockwise, and these are some arrows with some signs. Okay. So how ghost diagrams are related to nodes. So basically, suppose we have a given a diagram of trefoil node, then we can construct a ghost diagram corresponding to it. So basically, we first need to parameterize the diagram. We put a star and we start moving in the direction of the orientation of the node. We label the crossings as 1, 2, and 3, and we write a code. So basically, uh, we start from the point star and we move along this arc. So we are going over the crossing 1. So we write 1 over, and the sign of the crossing is basically negative. So we write minus, and then we go to the second crossing, which is under crossing, and we are passing under the arc. So we write 2u minus, and similarly the rest. We keep on doing this unless we don't come back to this point star. And from this code we can draw ghost diagram. So this is just one component link. So basically we just need a one circle, and since here are three crossing points, so we label um, points over the circle as 1, 2, 3 in the sequence of this code. In the sequence of this code, and we join an arrow from over crossing to the under crossing. Okay, and since all these are negative crossings, and we label the arcs as minus. Uh, Sorry, our arrows as minus. So to study nodes in terms of ghost diagrams, we need some kind of equivalence relations over the ghost diagrams. So these are three sufficient moves which are sufficient to capture the node theory in terms of node diagrams. So the first corresponding to the administer move 1, and second is for second administer move, and the third administer move. So we know that from node diagrams we can go to the ghost diagrams, but the other way around is not true in classical node theory. So there are some ghost diagrams which cannot be realized by link diagram. So here is an example. We have an oriented circle, and we have two arrows with same sign. Then we try to draw a link diagram. So basically we first draw two crossings, one these two, then we try to join them. So basically we note that if we want to join them, then we have to pass through some points which are not actually crossings. So this is an example where we cannot draw a link diagram from the ghost diagram. So To overcome these things and to extend the study of nodes, so Professor Kaufman and Gostrov and Pollock and Vero define virtual nodes in terms of the gauss diagrams. So basically, by virtual link we mean equivalence classes of gauss diagrams. And moreover, there is a topological interpretation of these virtual links. So we can think of links in the thickened sphere where the sphere is compact and oriented. So to define the equivalence of these virtual links, so basically we will study these links up to ambient isotropy, addition and removal of the handles, and orientation preserving homeomorphism of the surfaces. So here is just an illustration. So we have a node uh, diagram in the torus. Um, and if we take a projection it over on the plane, we see that we have some kind of crossing, which is actually not a real crossing in the torus. So this crossing is basically due to the genus of the surface. So it was proved by Cooperberg that every virtual link has a unique representative in a minimal genus surface up to ambient isotopy. So this basically means that the classical node theory is basically subcase of the virtual node theory. So we have defined virtual node groups. Um, we have given different methods. Actually, the how we arise these things, that basically we were studying some representation of braid groups, and we define virtual node groups using different methods. So I will just illustrate here one method using gauss diagrams. So suppose we have a gauss diagram D with some m circles. We label each circle as V1, V2, and Vm, and we cut the circles at each endpoint of the arrows, and we label the arcs in the gauss diagram as x1, x2, and xn. And we define a group pi d by through a presentation where x1, x2, xn are basically the labeling of the arcs in the gauss diagram, and v1, v2, vm corresponding to the circles in the gauss diagram. And we add some relations. So the relations for each arrow we add two relations, and these are portions of the gauss diagram. So this is ith, this arc belongs to the ith gauss diagram, and this arc belongs to the jth gauss diagram, and we have labeling them as b, c, and ad, and we add two relations for each arrow. Similarly, if the arrow is negative, we add these kind of relations, and additionally we add more relations. So we want that vi and vj commutes for each I and j. Okay. So now I will define mark gauss diagrams. So I will just abbreviate them as MGD. So basically these are just gauss diagrams with additional information that we add some nodes which have some signs plus or minus signs on the gauss diagram. So here is an example. So we have this gauss diagram, and we add two nodes plus and minus with signs, and as we have done in gauss diagrams, we can draw a virtual node diagram. So we can similarly here draw these kinds of diagrams, and we name this diagram as marked virtual link diagrams. And to study these diagrams, we have defined some equivalence relations. So the first is that of this, and the second is this. So basically, here eta means the sign of the node, means it can be plus or minus, and for applying this relation, we want that these two arcs belong to the same component, and even in the second case also. But here the sign of nodes are actually opposite. So additionally with this, we also allow the Redminster moves over the marked ghost over the ghost diagrams. So now we will define our groups. We will associate groups to each marked ghost diagrams. So the idea is same as we have done in the ghost diagram. So basically we will first cut each circle at the end point of arrows, and also we also cut them at node points also, and then we label the arcs, and we add the relations of these types for each arrow, and for each node we add the relation, this relation. So here eta is basically the sign of the node, and this is basically ith this arc belongs to the ith part of the circle, And so we add a relation B is equal to A, V, I, N. And we define the group pi d to a given marked Gauss diagram, which is generated by x1, x2, and xn, and v1, v2, n, and these correspond to the number of circles in the given diagram. And the relations are these, basically these relations for arrows and the nodes. And we add one additional relations of commutativity of each vi and vj. So one can actually check that the Gauss diagrams are sitting properly sitting inside these marked Gauss diagrams. So basically it is a kind of generalization, but it is a combinatorial generalization. And the way we have defined this group is basically it will coincide with the group we have defined previously. And moreover, these groups are basically generalization of the groups defined by Kaufman for virtual nodes. So now here we'll go through some definition. So we have some integer n, positive integer. We define a group G to be a CM group. If we can write it in terms of presentation y and r, where y is a set of generators, it consists of two sets, basically x and vn, where x is a collection of n elements and vm is a collection of m elements. And we add the relations of commutativity for each vi and vj. Sorry, here is vj, okay. And the second is the relation of these kinds. Basically, these are conjugation relations where these wij's are some words in the set y and plus minus 1. And minus 1 basically means we are considering the formula inverses. Now we define a group, CM group, to be irreducible if its abelianization is of rank 2m. So given a m, we wanted that its abelianization is of rank 2m. So basically CM groups are basically a special class of C groups which was defined by Professor Kulikov. Okay. So we have proved that if we are given any irreducible C1 presentation of deficiency only 1 and 2, then we can find a marked Gauss diagram whose group is isomorphic to the given one. Okay. So basically, one can think of this Gauss diagram as a kind of completion to achieve these CM groups, basically. Okay. The next is the problem. We formulate that for let G be a finitely generated group generated by mu and conjugates of mu. So the question is, can we find a marked Gauss diagram and a Horn-2 homomorphism from the group pi d to the group G, such that the image of meridian is mu and image of V. So V corresponds to the basically the one circle in the Gauss diagram is mu. So here I am saying meridian. So I am not explained here what I mean by meridian for the Mark-Gauss diagram. So basically we have given a combinatorial definition of the meridians and longitudes for these diagrams. And then we define the peripheral structure as the conjugacy classes. So, but I am going through these things. So basically it is simple. Just for meridian, we just take a arc over the Gauss diagram as a meridian, and then we move along the arc, move along the circle in the Gauss diagram. And for each arrow and node, we add some kind of words, and then we write the longitude in terms of that. So we have proved that. So basically, lambda g is basically the set, the elements in the set G, which are images of the longitude. Okay. So the question is whether we can find such basically representations or not. So we have proved that yes, we can find these such representations, and lambda g, the set lambda g is basically a subgroup of G. Okay. Yeah. Thanks for the attention. Any questions?
Well, so far today's talk turned out to be very short. So please let's use as much time as possible for questions. So I have written several questions in the chat line. So please unmute your microphones and ask as many questions as possible.
Vishal,
yes.
I cannot see your chat.
I I asked the speaker personally. So one of
Uh,
my questions is as follows. At some point, I used some construction of the quandle for long virtual knots by using two operations with early overcrossing and early undercrossing. So I was using two different operations, and actually they have to be compatible in a certain sense, which is given in my book or any of my articles. So I wonder whether your manipulations with groups and possibly with with residually finite groups and other groups can give us examples for classical knots. So the idea, the motivation is as follows. For long virtual knots, I quite easily proved that they are not invertible and that they actually do not commute. And now I would like to look at long classical knots. And I would be happy to get a free a free maybe criterion of invertibility. In order to do that, it would be good to have a group which well changes when we change the direction. So that's why I introduced some such things. But in order to get it, well, we need to set some conditions to be satisfied. I suggest you to look at these. So colleagues, please ask more questions, more and give more comments. Manpreet, can you please
Professor, I'm not able to hear properly.
Scroll back your slides and comment on unsolved problems and various questions. I think unsolved problems would be okay if K is fine. By the
Which
way,
page should I go?
what is the relation? Between various groups you can get from knots and simple groups? Can you get any simple group invariance of knots?
Professor, I'm not able to hear you clearly.
Can you you consider groups which are generated by conjugates of meridians. Can we get nice knot invariance from simple groups? There was some. Okay. No, it's strange. Colleagues, can you hear me?
Yeah.
I can hear you, but your voice sound is very low.
Yes.
Yeah, okay. Colleagues, so please, Roger, maybe you can comment on this work. It was so quick.
Well, I mean, yeah, it's nice to see ordering of quandles, which is something I've never thought about before. But obviously, it's good that it relates to the work of Rolfson, who's very keen on ordering of groups and so on. Well, a nice talk, nicely presented. I don't mind it being short.
Yes, so there is one question on the chat line. You considered link quandle and it's analogous to not quandle. Yeah, so I don't know who asked it about link quandles. Yes, there are more questions on the chat line. Manpreet, please read them. Okay. So any more? So Manpreet, there are questions on the chat line. So please ask more questions.
Yes, sir. Yes, for the construction for the link quandle is similar to that of not quandle. So basically, in link quandle, we have some say m component link. Then you just take the tubular neighborhood of each component, and then you take the complement space is basically the closure of the tubular neighborhoods in the three sphere. Uh, then you just define the set qk as the homotopy classes of paths whose initial points lie on the tubular neighborhoods, and the final point is some say point x naught in the space. And during the homotopy, your initial point can only move over the tubular neighborhood of just one component. Means you cannot slide, you cannot pick one means one path from one component to the another path. That is not allowed. But you can move freely your path over the boundary of the tubular neighborhood in one component, but you cannot move to the other components.
Then may I ask you to move to the page about a link group and link quandle?
Yes, right. Here.
There was a kind of statement. Link quandle is isomorphic to the isomorphic to the cofactor
This one.
quandle. I mean, excuse me.
So here is the statement for link quandles for non-separate links.
I've got I've got a question. Maybe it's not a question, but a sort of research project. Actually, virtual knots are known to behave like classical links. So the reason is that we can distinguish between different types of crossings, and we can extract some fundamental group action on that. So here you mentioned lots of various groups or group actions. And I wonder whether classical knots can somehow behave like links. I mean, can we somehow use the power of the fundamental group or of the knot quandle in order to get a map from knots to links, or at least some way of enhancing knots by some information which would freely give you such nice things like self-linking number or whatever.
Okay.
Okay, any further questions?
Could you
yeah,
share the material for this thing? Means the virtual nodes behave like classical links.
Oh yeah, sure. Yeah, sure. Well, first of all, you can look at my book, Invariants and Pictures. Okay, we can look at that separately. Any further questions? Well, okay, if it's not the case, so let's thank the speaker. Well, so